Before Erwin Schrödinger was born, before anyone could imagine a cat that might be both alive and dead, the universe seemed like a clockwork masterpiece. Every planet, every stone, every atom was thought to move with the same precision as gears turning in a perfectly engineered machine. Humanity had finally decoded the language of the cosmos, and the words were written in mathematics. Isaac Newton's laws had reigned for more than 2 centuries, shaping everything from the trajectory of cannonballs to the orbits of the planets. The universe was predictable, measurable, and logical. It was a place where certainty lived and mystery seemed to have surrendered. Scientists believed that with enough data, they could predict the entire future, a dream that seemed within reach. The 18th and 19th centuries were centuries of confidence. Newton had shown that gravity bound the heavens to the earth, that the same force that made apples fall kept the moon in its orbit. Galileo had taught the world how to observe. Newton taught it how to calculate. Determinism became the holy creed of science. Pierre-Simon Laplace, a French mathematician, imagined a hypothetical being, later called Laplace's demon, who, if it knew the position and motion of every particle in the universe, could predict the past and the future with absolute certainty. There was no room for chance, no room for uncertainty. Everything, from the fall of a leaf to the collapse of a star, was predetermined by the grand machinery of nature. It was an elegant, comforting illusion of order. By the late 19th century, physics had become a monument of precision. Engineers could design bridges that would stand for centuries. Astronomers could predict eclipses down to the second, and chemists were beginning to decode the patterns of elements in the periodic table. The confidence of science was unmatched. The British physicist Lord Kelvin famously declared that physics was nearly complete. All that remained were a few small clouds on the horizon. He meant a few puzzling phenomena that didn't quite fit: the blackbody radiation problem and the photoelectric effect. Small clouds, he said. But those small clouds would soon erupt into a storm that would rewrite reality itself. The world before Schrödinger was not just ruled by classical physics. It was defined by it. The human imagination saw nature as a grand symphony conducted by precise mathematical laws. Everything followed the rhythm of causality. If you knew the initial note, you could predict the final chord. Determinism was not merely a belief. It was the foundation of civilization's confidence. Steam engines, telegraphs, electric lamps. All the marvels of the industrial age were proof that the universe obeyed human understanding. The scientist's laboratory became a temple of control. Experimentation and observation were sacred rituals to confirm that the laws of motion were absolute and eternal. But even as the Industrial Revolution roared forward, cracks began to appear in the foundation of classical certainty. Electricity and magnetism, once thought to be separate forces, were unified by James Clerk Maxwell into a single framework: electromagnetism. His equations revealed that light itself was an electromagnetic wave. Suddenly, the universe seemed more mysterious. Invisible fields filled all of space. But even Maxwell's brilliance fit neatly into the deterministic order of the time. His equations were continuous, smooth, and predictable. They told of waves traveling endlessly through the ether, a substance scientists believed filled the void between stars. Space, it seemed, could not be empty. The ether was the medium through which light and electromagnetic waves moved, invisible yet indispensable. Then came an unexpected blow. In 1887, Albert Michelson and Edward Morley tried to detect the ether, to measure the Earth's motion through it, but found nothing. The ether, it seemed, didn't exist. Space was empty, yet Maxwell's equations still worked perfectly. It was as though nature were whispering that something fundamental about human perception was flawed. Still, the old faith persisted. Scientists believed the missing answers would eventually appear within the comfortable structure of classical theory. They were wrong. The dawn of the 20th century arrived with strange light. Wilhelm Röntgen discovered X-rays. J.J. Thomson found the electron, and Max Planck stumbled upon something that defied all reason. Energy, it turned out, was not continuous. It came in small, discrete packets. Quanta, Planck's discovery in 1900, was the first crack in the mirror of determinism. But he himself resisted its meaning. He treated the quantum as a mere mathematical trick, a temporary fix. The idea that nature itself might be quantized, that light and energy came in indivisible chunks, was too radical to accept. Yet the universe had spoken its first quantum word. For more than 200 years, physics had treated reality as a tapestry of continuous threads woven together without breaks. Now, Planck's discovery suggested that the threads might be made of distinct pieces. The very fabric of the cosmos was granular. Light, once thought to be a smooth wave, now behaved like particles in certain experiments. Matter, once thought to be solid and local, began to dissolve into clouds of probability. Still, the guardians of the old world clung to Newton's laws. They saw these new discoveries as temporary exceptions to a rule that must somehow still hold. In the universities of Europe, Göttingen, Cambridge, Vienna, students learned physics from the masters who still worshipped Newton's order. Reality, they were told, was objective, separate from the observer. Measurements simply revealed what already existed. The observer played no part. The scientist was a detached witness, not a participant in the cosmic play. It was a worldview that suited the rational spirit of the age, clean, mechanical, impersonal, and yet beneath the surface, new forces were gathering, invisible and unstoppable. The atom, once thought to be the indivisible building block of matter, was beginning to show its inner secrets. Electrons orbited nuclei like planets around a sun, but those orbits didn't behave as expected. When atoms emitted light, they did so in sharp, discrete lines of color, not in smooth, continuous rainbows. It was as if atoms played specific musical notes, rather than sliding across a scale. This spectral fingerprint puzzled everyone. Why did atoms radiate energy in such precise steps? Classical physics could not explain it. Something deeper, stranger was at work. Niels Bohr, a Danish physicist, proposed a daring model. Perhaps electrons could only occupy certain allowed orbits, jumping between them by absorbing or releasing quanta of energy. It was an audacious attempt to blend Planck's quantum idea with the old planetary picture of the atom. Bohr's model worked beautifully for hydrogen, but it was incomplete. It was as if the universe had given humanity a glimpse of a secret it was not yet ready to understand. The equations worked, but no one could explain why. As this new quantum puzzle unfolded, Europe was a continent of contradictions, intellectually alive, politically fragile, artistically daring. The world was changing rapidly, and so was its understanding of itself. The same decade that gave birth to the theory of relativity, where time and space bent under the weight of gravity, also gave rise to the first whispers of uncertainty in the quantum world. Einstein's relativity shattered the notion of absolute time and space, but it still preserved determinism. In his universe, cause and effect still ruled. Light might curve, clocks might slow, but the universe still obeyed a strict logic. The quantum realm, however, threatened to erase that logic entirely. In the laboratories of Berlin, Copenhagen, and Zurich, experiments were revealing a new kind of behavior. Electrons that acted both like particles and waves, photons that interfered with themselves, and outcomes that could only be described by probabilities, not certainties. The old vision of the universe as a giant machine began to tremble. The deterministic dream of Newton was fading like an echo, replaced by a new whisper. The universe might not be a machine at all, but a symphony of possibilities. It was in this twilight of certainty that Erwin Schrödinger would one day arrive. But before his equation could be written, before his cat could be imagined, humanity had to watch the old order collapse. The fall of classical physics was not sudden. It was slow, painful, and poetic. Scientists clung to their beliefs like sailors to a sinking ship, even as experiment after experiment revealed that the universe did not care for their definitions. Light refused to behave. Matter refused to sit still. Reality itself refused to remain obedient. The human mind, so proud of its ability to measure and predict, found itself facing an abyss of unknowing. What did it mean for something to exist before being observed? Could energy appear and disappear like ghosts in a haunted laboratory? What was an atom, really? The answers would not come easily. They would emerge from the minds of dreamers, rebels, and visionaries, from men like Planck, Einstein, Bohr, Heisenberg, and finally Schrödinger, who dared to believe that reality was not what it seemed. The world before Schrödinger was an age of confidence that mistook precision for truth. It was a world that believed in fixed boundaries between science and philosophy, between observer and observed, between fact and faith. But every new discovery blurred those lines. The equations of Newton were still powerful, but they no longer ruled alone. There was something deeper beneath them, something unpredictable and alive. The clockwork universe was cracking, and through those cracks the quantum light was beginning to shine. Men like Lord Kelvin and Heinrich Hertz had seen themselves as masters of a stable world. They believed that once all the constants were measured, the universe would be fully known. Yet as Planck's quantum appeared, as electrons misbehaved, and as space and time themselves twisted under Einstein's relativity, the dream of total knowledge dissolved into mystery. The classical physicists' God was one of order and predictability. The quantum God, if there was one, spoke in riddles of probability and chance. And so, as the 19th century gave way to the 20th, a new kind of scientist was needed, one who could embrace both reason and wonder, mathematics and imagination. Schrödinger would be that scientist. He would step into the ruins of the classical world view and build a new temple of understanding. But before he could do that, the old world had to fall completely. It had to admit that its foundations were illusions, its certainties fragile. The first keynote in the story of Schrödinger is not about equations or experiments. It is about the death of certainty, the slow, quiet realization that the universe was not a predictable clock, but a living question. By the time the young Erwin Schrödinger began studying physics in Vienna, the scientific landscape was already trembling. The laws he learned were still Newtonian in flavor, but the questions were new, uneasy, and unresolved. The air of Vienna, rich with music and philosophy, carried with it the sense that knowledge was no longer solid. The old boundaries between science and metaphysics were dissolving. The city's coffee houses were filled with writers and thinkers debating reality, consciousness, and existence, the very themes that would one day haunt Schrödinger's own mind. It was a world poised between two ages, the mechanical and the mysterious. This was the universe before the cat, before the equation, before the paradox. A world still clinging to its certainties, unaware that one quiet Austrian would soon take a pen and, with a single wave equation, forever change what humanity meant when it said the word real. As the 20th century unfolded, the old pillars of certainty were still standing, but the cracks had widened. Scientists, for generations raised on Newton's logic, were now forced to look into a world that seemed to slip through the fingers of reason. Classical mechanics could no longer explain why hot metal glowed red before turning white, why ultraviolet light could knock electrons loose from a metal surface, or why atoms radiated light in exact, discrete colors. Every new experiment was a confession that the universe refused to be tamed by old equations. Max Planck had tried to make peace with the chaos. He did not want to destroy classical physics, he wanted to save it. But when he introduced the idea of energy quanta, he opened a door that could never be closed. Behind that door waited a new kind of reality, fragmented, statistical, and alive with uncertainty. The beauty of determinism gave way to the elegance of probability, and probability, though mathematically pure, was philosophically unsettling. What kind of universe hides its truths behind dice throws? Albert Einstein, the young patent clerk from Bern, entered the scene with a mind ablaze. In 1905, his annus mirabilis, his miraculous year, he published papers that shattered every illusion left standing. He showed that light itself could behave like particles, quanta of energy later called photons, and that mass and energy were interchangeable. Space and time, once eternal backdrops for motion, were revealed to be flexible, bending and stretching under the weight of gravity. It was as if nature had been living behind a painted curtain, and Einstein had torn it down to reveal a new stage altogether. Yet even he was disturbed by where the quantum hints were leading. He wanted order, not chaos, an intelligible cosmos, not one ruled by chance in laboratories across Europe. Younger scientists were becoming accustomed to the discomfort of paradox. They no longer demanded that nature obey intuition. They were ready to follow the mathematics wherever it led. In Copenhagen, Niels Bohr built his vision of the atom around the quantum leap, electrons jumping between orbits in sudden bursts of energy. The model worked astonishingly well but made little sense in classical terms. What made an electron decide to leap? Why one orbit and not another? The questions had no answers that fit the old mechanical worldview. Bohr's atom was an act of faith, and faith was not supposed to belong in physics. Still, progress came at a dizzying pace. Louis de Broglie, a French aristocrat with the soul of a poet, proposed that matter itself behaved like a wave. Electrons, he said, were not tiny spheres, but ripples in an invisible ocean of probability. A century of certainty began to dissolve into shimmering possibility. The laboratory became a stage for paradoxes. When electrons were fired through two slits, they interfered with themselves like waves, yet when measured, they arrived one by one like particles. It was as if they existed in many places at once, until someone looked. Observation no longer meant passive watching, it meant participation. The observer had entered the story in this shifting landscape. The name Erwin Schrödinger was not yet legendary. He was a quiet Austrian, elegant in thought and restless in spirit, a man drawn equally to physics, philosophy, and the poetry of existence. He studied the works of Boltzmann, Einstein, and Planck, feeling both admiration and unease. The quantum theory, though powerful, seemed fragmented, a collection of rules rather than a complete understanding. Schrödinger yearned for harmony. He wanted an equation that would restore the beauty of continuity without denying the truth of the quantum. He wanted to reconcile the waves of de Broglie with the probabilities of Planck. Somewhere inside him burned the conviction that nature could not be as chaotic as it appeared, that beneath the randomness lay an order waiting to be revealed. Europe, meanwhile, was still haunted by the aftershocks of war. The First World War had torn the continent apart, leaving behind a generation disillusioned by destruction and yearning for meaning. Science, too, had lost its innocence. The same physics that powered progress had built weapons of unprecedented devastation. In the ruins of Vienna, a cultural and intellectual renaissance took shape. A desperate attempt to find order in chaos, music, philosophy, and science converged in the cafes and lecture halls. In that ferment, Schrödinger's mind roamed freely, absorbing ideas about unity, consciousness, and the hidden patterns behind appearances. He read Indian philosophy and the Upanishads, where he found echoes of what he felt in physics, that the observer and the observed might be one and the same. Long before he wrote his famous equation, he was already searching for the bridge between matter and mind. The turning point came in the mid-1920s. Werner Heisenberg, working under Bohr in Copenhagen, devised a new way to describe atomic behavior, matrix mechanics. It was powerful but abstract, filled with arrays of numbers representing transitions between quantum states. It predicted results that matched experiments perfectly, yet few could grasp what the mathematics meant physically. Schrödinger admired Heisenberg's brilliance but felt unsatisfied. He wanted a picture, something continuous, visual, intuitive. He believed that de Broglie's idea of matter waves was the missing key. If electrons could be seen as waves rather than points, perhaps their strange behavior would become natural. But what governed those waves? What was their law of motion? In the winter of 1925, seeking clarity and solitude, Schrödinger retreated to a small alpine resort in Arosa, Switzerland. The mountains were blanketed in snow, and the air was sharp and silent, perfect for thought. There, with notebooks, equations, and his beloved cat nearby, he began to write. Day after day, he filled pages with symbols and speculations, searching for a single equation that could unite the quantum world into one harmonious theory. The beauty of mathematics guided him like a melody. Finally, in early 1926, he found it, an equation so elegant that it seemed less discovered than revealed. The Schrödinger wave equation was born. It was a moment of quiet triumph, though few could grasp its significance. The equation described how the wave function, the mathematical essence of a quantum system, evolved through time. It was the heartbeat of the microscopic world. Every electron, every atom, every molecule danced to its rhythm. Determinism had not died after all. It had been transformed. The certainty of positions and velocities was gone, replaced by the certainty of probabilities. The world was no longer made of objects but of waves, invisible patterns of possibility spreading through space. Schrödinger's equation brought music back into physics. The universe was a grand symphony of overlapping wave functions, each resonating with its own frequency. When atoms emitted light, it was not a mystery, but a natural consequence of these standing waves shifting from one pattern to another. The sharp spectral lines that had baffled physicists for decades were now notes in the cosmic melody. For a brief moment, harmony returned. Schrödinger had restored continuity to a fragmented world. But with harmony came confusion. What was the wave function really? Was it a physical wave like ripples on water, or merely a mathematical abstraction representing knowledge? Schrödinger believed the waves were real, that they described the actual state of matter. Yet others, including Heisenberg and Bohr, argued that the wave function represented only probabilities, not physical reality itself. The clash of interpretations was inevitable. Physics had become philosophy again. Bohr's Copenhagen interpretation insisted that the wave function was not a picture of what is, but a tool to predict what will be observed. Reality, in this view, did not exist in a definite state until measurement forced it to choose. Schrödinger recoiled at this notion. He wanted the universe to be real, even when unobserved, to expose what he saw as the absurdity of Copenhagen's logic. He imagined his famous cat, a creature trapped in a box, suspended between life and death until someone looked inside. The thought experiment was a protest, a cry against the surrender of realism. Yet the world embraced it as a symbol of quantum mystery. The cat became immortal, both alive and dead, in the imagination of humanity. Behind the symbolism, the conflict ran deeper. The old dream of classical physics, that reality was objective and independent of observation, was dying. Schrödinger's equation had revealed a universe of pure potential, one that collapsed into actuality only when touched by awareness. The observer had become part of the experiment. The boundary between mind and matter was blurring. For centuries, humans had believed they stood apart from nature, watching from a safe distance. Now, quantum theory told them they were participants in creation itself. Even as debates raged, Schrödinger's work spread like wildfire. It explained hydrogen better than Bohr's model, predicted new atomic behaviors, and became the cornerstone of quantum mechanics. Dirac, Pauli, Born, and others expanded upon it, weaving an intricate tapestry of equations that described the unseen world with unmatched precision. The results were undeniable. Transistors, lasers, nuclear energy, and quantum computers would all grow from the seed Schrödinger had planted. Yet the philosophical unease never faded. What did it mean for a wave of probability to collapse? What did observation truly do? Schrödinger's cat never left the box. It lived on in every discussion about reality, consciousness, and truth. Looking back, one can see the full arc of transformation. The world that began with Newton's certainty ended with Schrödinger's ambiguity. But within that ambiguity lay a deeper beauty. The universe was not mechanical after all, it was creative. Its laws did not dictate, they permitted infinite possibilities, branching realities, and the miraculous emergence of consciousness itself. Schrödinger had not destroyed order. He had revealed that order is fluid, dynamic, alive. In the classrooms and laboratories of today, the equations of Newton and Schrödinger sit side by side. One rules the macroscopic, the other the microscopic. Together they tell the story of humanity's evolving relationship with truth, from certainty to curiosity, from control to participation. The physicists of the classical age looked at the stars and saw machinery. Schrödinger looked at the atom and saw mystery. And in doing so, he reminded the world that knowledge is not a wall to be finished, but a horizon to be forever pursued. The journey that began with falling apples ended with quantum cats, and yet the question remains the same. What is reality? Schrödinger never claimed to know. He only offered the most honest answer science has ever given, that reality is a wave of possibility waiting to become. He changed not only physics but philosophy, not only equations but imagination. The deterministic universe died, and in its place rose a universe of wonder, one where observation breathes life into being, and where the quiet curiosity of a single mind can alter the meaning of existence itself. Erwin Schrödinger, the reluctant revolutionary, did not seek to rewrite reality, he sought to understand it. But in that search, he became the architect of a new worldview, one where the boundaries between the seen and the unseen, the real and the possible, are as delicate and profound as the whisper of a wave moving through the void. His legacy is not merely scientific, it is human. It is the story of how a man looked into the smallest depths of creation and discovered the infinite. At the turn of the 20th century, the world stood on the edge of revelation. The old order of physics still gleamed like polished marble, but deep beneath its surface, cracks had begun to spread. The certainties of Newton, the harmony of celestial mechanics, the precision of classical electromagnetism, all of them were beginning to falter under the weight of phenomena too strange to fit their logic. The universe, which for centuries had seemed like a vast, predictable clock, now began to whisper in riddles. In laboratories across Europe, light and matter refused to obey the rules that had once governed every atom of existence. What emerged from that defiance was not chaos, but something far more profound. A new reality where probability replaced predictability, and where uncertainty became not a flaw in human knowledge, but the very essence of nature itself. The story began quietly, with an experiment that seemed too simple to rewrite the laws of physics. In the late 19th century, scientists studied how heated objects emitted light, a phenomenon known as blackbody radiation. According to classical theory, as the temperature of an object rose, it should radiate more and more energy, especially at shorter wavelengths. But experiments showed a bizarre contradiction. At high frequencies, the predicted energy became infinite. It was called the ultraviolet catastrophe, a poetic name for the failure of reason itself. No matter how refined the mathematics became, classical physics could not explain why objects glowed red, then orange, then white, but never ultraviolet blue at normal temperatures. Something invisible was breaking the logic of nature's equations. In 1900, Max Planck, an unassuming German physicist with the soul of a mathematician, stepped forward to solve the puzzle. Desperate to match theory with observation, he made a bold assumption. Energy was not continuous, as everyone believed, but came in tiny packets, which he called quanta. Energy could be emitted or absorbed only in these discrete amounts, proportional to a new constant he introduced, h, the quantum of action. To Planck, this was a temporary mathematical trick, a bridge between ignorance and clarity. He did not realize he had torn open the door to a new universe. In that moment, the smooth, continuous fabric of reality became grainy. Energy, the most fundamental element of the cosmos, no longer flowed like water, it pulsed like a heartbeat. For a time, no one grasped the depth of what Planck had done. The scientific world accepted his formula, but ignored its implications. Even Planck himself resisted the philosophical consequences. Yet just 5 years later, a young patent clerk named Albert Einstein took the quantum further than anyone dared. In 1905, while working in the quiet of his Swiss office, Einstein proposed that light itself came in particles, tiny packets of energy later called photons. It was the ultimate act of rebellion against the wave theory of light that had reigned since the days of Maxwell. Light, Einstein said, was both wave and particle. It could spread through space as a wave, yet strike metal as if it were a stream of bullets. His explanation of the photoelectric effect, how light could knock electrons from metal, earned him the Nobel Prize and changed the world forever. The duality of light was the first crack in the mirror of certainty. Einstein's discovery was more than an equation. It was a philosophical earthquake. The boundaries between matter and energy, between wave and particle, began to dissolve. Yet if light could behave like matter, might matter also behave like light? The question lay dormant for nearly 2 decades until a French prince turned physicist, Louis de Broglie, dared to answer it. In 1924, de Broglie proposed that all matter had a wave-like nature, that electrons, protons, even entire atoms could behave like waves. He imagined the universe as a vast sea of undulating probability, where particles were not points but patterns. His doctoral thesis, elegant and radical, was initially met with disbelief. But soon experiments proved him right. When electrons were fired through a double slit, they produced the same interference pattern as light waves. Matter, it seemed, could be in many places at once. The microscopic world did not obey the same logic as the macroscopic one. The very idea of location had become uncertain. What was emerging was not merely a new branch of physics, it was a new worldview. The comforting determinism of Newton's universe was giving way to a quantum landscape ruled by chance, duality, and mystery. The laws that governed billiard balls, planets, and pendulums could not describe the dance of electrons. Classical mechanics had assumed that if one knew the present precisely, one could predict the future exactly. But the quantum world laughed at such arrogance. The more precisely one tried to measure an electron's position, the less precisely one could know its momentum. This strange limitation, articulated later by Werner Heisenberg in 1927, became known as the uncertainty principle. It was not a flaw in instruments or human perception. It was a fundamental feature of reality. Nature, at its core, refused to be pinned down. Heisenberg's revelation was born not in a laboratory, but in the restless mind of a young man haunted by paradox. Working late into the night on the island of Helgoland, suffering from hay fever and insomnia, he sought a mathematical language that could describe atomic behavior without relying on impossible visualizations. He replaced orbits and trajectories with arrays of numbers, matrices, that represented transitions between quantum states. When he showed his results to Niels Bohr, the great Danish philosopher-physicist, Bohr immediately recognized their power. Together they began to craft a new interpretation of reality, one that placed observation, not objective existence, at the center. The act of measurement, they said, did not merely reveal reality, it helped create it. The observer was no longer separate from the observed. The birth of quantum uncertainty shattered the last illusion of control. The universe was no longer a story written from beginning to end. It was an improvisation unfolding in real time. At every scale, particles existed not as things but as possibilities. A particle was not here or there, it was a superposition of both, a cloud of potential that only solidified when someone looked. Reality itself became participatory. To watch was to influence, to measure was to disturb. In this new cosmos, knowledge was not passive, it was creative. The implications were dizzying. Einstein, who had once illuminated the quantum mystery, now became its most famous skeptic. He could not accept that God played dice with the universe. He believed that hidden variables must exist, undiscovered laws that would restore certainty. But every experiment seemed to mock that hope. When physicists tried to pin down quantum particles, the very act of observation changed their behavior. It was as though the universe hid its secrets behind a mirror that blurred whenever one tried to see too clearly. Reality was no longer something to be found, it was something to be experienced. Meanwhile, Erwin Schrödinger, watching these developments with both admiration and unease, felt the need to reconcile the strange duality of matter and light. He believed the quantum world was not ruled by randomness, but by deeper waves of order, waves that could be described precisely if only one could find the right equation. While Heisenberg's matrices represented discontinuity, Schrödinger sought continuity. He imagined a universe where electrons moved not in chaotic jumps but in smooth, harmonious patterns, like vibrations of sound. His search for such an equation would soon lead him to write one of the most important mathematical expressions in history, the Schrödinger equation, and with it to reveal that uncertainty was not disorder but the rhythm of creation itself. But before that harmony could emerge, uncertainty had to take its full shape. In the 1920s, experiments on atomic emission and absorption confirmed that energy changes occurred in abrupt steps. There was no smooth transition from one state to another. The microscopic world leaped rather than flowed. Bohr described these leaps as quantum jumps, a phrase that captured both their mystery and their beauty. An atom did not gradually release light. It suddenly shifted from one energy level to another, releasing a photon in the process. Between those levels it existed in a kind of limbo, neither here nor there, neither this nor that. The atom lived in superposition, the twilight between possibilities. For philosophers, this was an earthquake. For centuries, knowledge had been built on the assumption that every effect had a definite cause. Now, cause and effect had been replaced by probability and observation. Determinism was dethroned by indeterminacy. Yet this indeterminacy was not chaos. It followed laws of its own, precise and calculable. The mathematics of quantum theory could predict outcomes with astonishing accuracy, even if it could never predict individual events. It was as if nature rolled dice, but those dice obeyed mathematical rules no human could defy. The double-slit experiment became the emblem of this new world. When scientists fired a beam of electrons through two narrow slits and observed the pattern on a screen, they found that each electron behaved like a wave, interfering with itself to create bright and dark fringes. But when they tried to observe which slit the electron passed through, the interference pattern vanished. The act of measurement collapsed the wave of probability into a single outcome. The electron chose a path only when forced to decide. Before observation, it existed in all possible paths simultaneously. This experiment, simple yet profound, remains the purest demonstration of quantum uncertainty, the idea that reality is not definite until it is witnessed. To those raised in the age of Newton, this was madness. How could something exist in multiple states at once? How could mere observation change what was real? Yet experiment after experiment confirmed the same result. Reality, it seemed, was a canvas that painted itself only when someone looked. Between observation and existence lay an invisible frontier where possibility reigned, and at that frontier human understanding trembled. By the late 1920s, the quantum revolution was unstoppable. Heisenberg, Bohr, Born, Pauli, Dirac, and Schrödinger were not just scientists, they were explorers of a new dimension of thought. The old world had measured space and time. The new one measured uncertainty and potential. The equations of the quantum realm revealed that the universe was not made of things, but of relationships, connections between observer, object, and event. What existed was not an independent world, but a web of interactions, flickering in and out of being like sparks in a storm. Even the language of physics changed. Words like position, momentum, and trajectory lost their meaning. In their place came wave function, superposition, and probability amplitude. The vocabulary of certainty gave way to the poetry of possibility. Physicists were no longer describing what is, but what may be. The mathematics spoke of infinite potential states, all coexisting until one was chosen by measurement. The quantum world had no past or future in the classical sense. It had only unfolding moments of realization. And yet within this uncertainty lay the seeds of everything that defines modern existence. Transistors, lasers, quantum computers, all trace their lineage to the trembling foundation of quantum theory. Every flash of light from a screen, every whisper of an electron through a circuit, carries the signature of uncertainty. What began as a philosophical riddle became the architecture of the modern world. Uncertainty was not an enemy of progress. It was its engine. The birth of quantum uncertainty did not destroy order, it redefined it. It revealed that reality was not a static picture but a living process, continuously shaped by observation and interaction. It taught humanity that knowledge is never absolute, that every measurement is also a choice, and that truth, at its core, is dynamic. The old dream of total prediction was gone forever, replaced by a humbler, more profound vision, a universe alive with freedom. And in that universe, Erwin Schrödinger would soon take center stage, standing at the intersection of mathematics and mystery, ready to translate the language of uncertainty into the music of waves. He would not erase the mystery, he would make it sing. When the storm of uncertainty swept through physics, it did not come with thunder or fire, it arrived quietly, on paper, in equations written by restless minds. By the middle of the 1920s, the very idea of what it meant to know something in science had been overturned. The world was no longer a machine to be measured, but a mystery to be witnessed. At the heart of that mystery stood a new language, one that spoke not of certainties, but of probabilities, not of objects, but of waves, and the man who would give that language its music was Erwin Schrödinger. In the months after Heisenberg introduced his strange matrix mechanics, the community of physicists was divided. The equations worked with ruthless precision, predicting spectral lines and atomic behaviors perfectly, yet no one could see what was happening inside the atom. There were no orbits, no pictures, no visual models, only symbols and transitions. For a generation raised on Newton's trajectories and Maxwell's fields, this abstraction felt like exile. Schrödinger, poetic by nature and aesthetic by instinct, longed for a vision he could see. He could not believe that reality was built from numbers without images, that nature was a book written in pure algebra. Somewhere, he felt, the atoms must still be singing a melody, a continuous wave, hidden beneath the chaos of quanta. So he began his search. Inspired by de Broglie's idea that matter behaved like waves, Schrödinger set out to find the mathematical law that governed those waves. In late 1925, he withdrew into solitude again, returning to the mountains, that quiet refuge where nature itself seemed to speak. For weeks he worked through equations by the light of oil lamps, drawing upon Planck's constant, de Broglie's wavelength, and the energy relations of classical mechanics. The breakthrough came when he imagined the electron not as a particle orbiting a nucleus, but as a standing wave, a resonance that wrapped around the atom like a vibrating string fixed at both ends. For such a wave to exist, it must satisfy a specific condition, a balance between its curvature and its energy. Out of that condition emerged an equation so elegant, so inevitable, that it seemed almost discovered by the universe itself, rather than invented by a man. That equation, psi-t, the wave function, would become the heartbeat of quantum mechanics. It described how the state of a system evolved over time, how probabilities swelled and faded like tides. In Schrödinger's formulation, every particle was a wave spread across space, and the square of its wave function gave the likelihood of finding it at any point. It was a vision both precise and mysterious. The atom as harmony, the electron as music. Determinism was not destroyed but transformed. The future could be predicted, not as a single path but as a spectrum of possibilities. When Schrödinger published his papers in 1926, the reaction was immediate and electric. Here, at last, was a picture. Smooth, continuous, comprehensible. The mathematics was clear, the predictions accurate, the imagery beautiful. The hydrogen atom yielded to the new method perfectly. Its spectral lines, once mysterious, now appeared as natural consequences of standing waves. Physicists who had struggled with Heisenberg's matrices breathed easier. Einstein praised the work as a return to sanity. Bohr admired its power. Though he knew it would challenge his own interpretation, the quantum world suddenly had shape again, but it was a shape made of probabilities. Yet beneath the applause lurked unease. What did the wave function really represent? Was it a tangible wave of matter rippling through space, or merely a mathematical tool for prediction? Schrödinger insisted it was real, a physical field describing the distribution of matter itself. But others, like Born and Heisenberg, argued otherwise. Max Born proposed that the wave function's magnitude squared was not a material density, but a probability density, a measure of likelihood, not substance. In that interpretation, the wave did not describe what is but what might be. Schrödinger resisted fiercely. He wanted a world that existed independently of observation, a universe that did not wait for the human gaze to take form. The debates grew fierce, blending physics with philosophy, mathematics with metaphysics. Bohr's Copenhagen school championed the radical view that measurement created reality. Until observed, a particle existed in a superposition of all possible states. Only when measured did it collapse into one. Schrödinger found this intolerable. To him, it sounded like sorcery dressed as science. To expose its absurdity, he imagined a cat locked in a box, its fate tied to the decay of a single atom. If the atom decayed, poison would be released, killing the cat. If not, the cat would live. According to quantum mechanics, until someone looked inside, the atom existed in a superposition of decayed and undecayed states, so the cat too must be both alive and dead. The image was grotesque, comic, and profound. It was meant as a critique, yet it became immortal, a metaphor for the strangeness of the quantum world and the limits of human understanding. The paradox of the cat captured the essence of uncertainty. It revealed that observation was not just a way of learning about the world, it was an event that changed the world. In the macroscopic realm, such effects were invisible, washed out by the sheer number of particles involved, but in the microscopic domain, every measurement mattered. The universe, it seemed, was not a stage where events unfolded independently of us. It was an interaction, a dialogue between consciousness and matter. To look was to participate. To ask a question was to alter the answer. For Schrödinger, this was not the reality he wanted. He yearned for unity, for an underlying wave of existence that connected everything. His interests reached beyond physics into philosophy, biology, and Eastern thought. In the Upanishads, he found a haunting idea, that all consciousness is one, that the observer and the observed are not separate. To him, this resonated with the quantum picture. Perhaps, he thought, the wave function was not merely a tool of measurement, but a reflection of the interconnectedness of all things. The same field that defined the electron might, in some distant way, define us. In his later writings, he spoke of life itself as a form of order sustained by quantum processes, a theme he would explore in his small but revolutionary book. What is life? Decades later, while philosophers wrestled with meaning, experimentalists embraced the power of the equations. Wave mechanics merged with matrix mechanics into a unified framework, the quantum mechanics we know today. Paul Dirac wove relativity into the mix, predicting antimatter. Wolfgang Pauli formulated the exclusion principle, explaining the structure of the periodic table, and everywhere, Schrödinger's CSI appeared, guiding calculations from chemistry to electronics. The atom had been conquered, at least mathematically. But every conquest brought new riddles. The deeper physicists probed, the stranger the world became. Particles could tunnel through barriers they should never cross. Electrons could entangle, their states linked across vast distances, reacting instantaneously to one another's changes. Einstein, horrified, called it spooky action at a distance. But experiments proved it real. Quantum entanglement defied every notion of locality and separateness. It was as if the universe, beneath the veil of space and time, was a single, unified whole. Schrödinger himself coined the term entanglement, recognizing in it both the beauty and the terror of the new physics. The waves of uncertainty were not confined to atoms, they rippled across the cosmos. By the 1930s, the pioneers of the quantum age were scattered across a world sliding toward war. Their discoveries had reshaped technology and philosophy alike, yet in their private letters and diaries, one finds a tone of melancholy. They had uncovered the mathematical skeleton of the universe, but not its soul. Schrödinger, weary of the endless debates over interpretation, withdrew from the spotlight, turning his thoughts increasingly toward the unity of life and consciousness. He had built the most precise equation ever written, yet its meaning remained suspended between realism and mystery. The world, meanwhile, embraced the practical side of the revolution. Quantum mechanics gave birth to semiconductors, lasers, nuclear energy, and the electronics that would one day define civilization. The uncertainty that once frightened philosophers became the foundation of progress. The dice that Einstein refused to accept turned out to be the building blocks of modern reality. The rules that governed the atom now governed the global world. Still, beneath the triumphs, a quiet question persisted. If reality at its smallest scale is uncertain, what does that mean for us? Are we products of randomness or participants in a cosmic order too subtle to perceive? The physicists could measure the probabilities, but they could not measure meaning. Schrödinger's wave function remained both a tool and a mystery, a bridge between numbers and existence. In later years, experiments grew more precise. Quantum interference was confirmed for ever larger particles, pushing the boundary between microscopic and macroscopic worlds. At what scale, scientists asked, does the cat stop being both alive and dead? No one could answer. The line between possibility and actuality seemed arbitrary, drawn not by nature but by human perception. The question of measurement, of collapse, of observation remained unsolved. Each generation of physicists inherited the same paradox. Quantum theory works flawlessly, yet no one fully understands what it means. And so uncertainty, once the enemy of reason, became its greatest ally. It humbled science, reminding humanity that knowledge is not possession but participation. It replaced arrogance with awe. It showed that the act of observing is inseparable from the act of being. Schrödinger's equation, written in the quiet of an alpine retreat, became the anthem of a universe where every particle sings a probability, every atom hums a harmony, and every observer adds a note to the symphony. The microscopic world did not break the laws of nature. It revealed them to be far more subtle than anyone had imagined. The rules were not broken, they were rewritten in a deeper language, one that only uncertainty could teach. Out of that uncertainty came the realization that the universe is not fixed but fluid, not determined but creative. Every flicker of light, every quantum jump, every breath of existence is a testament to that creativity. Erwin Schrödinger's legacy is not only the equation that bears his name, it is the understanding that mystery is not the opposite of knowledge but its foundation. He gave humanity the courage to live with ambiguity, to find beauty in probability, to accept that the smallest particles of matter are also the greatest poets of possibility. In doing so, he transformed science into something larger, a meditation on existence itself. The birth of quantum uncertainty was the birth of modern thought. It shattered the mirror of certainty and replaced it with a prism, scattering reality into infinite colors. Through that prism, the universe revealed its true face, not a rigid mechanism, but a living wave of potential. Schrödinger, standing at its edge, listened to the hum of creation and wrote down its song. In the early decades of the 20th century, when science trembled between certainty and chaos, one figure stood at the center of that fragile balance: Erwin Schrödinger. He was not a man of laboratories and noise, but of silence and reflection. His genius was not only mathematical, it was philosophical, musical, and profoundly human. He belonged to a generation of thinkers who stared into the abyss of the quantum world and refused to look away. For Schrödinger, physics was never a mere collection of formulas. It was a mirror for existence itself, a way to ask who we are in a universe that no longer obeyed the laws of reason. He was born in Vienna in 1887, in an age when knowledge seemed secure. The world he entered was still Newtonian, a world of continuity and clarity, where time was absolute and cause followed effect with clock-like precision. His childhood unfolded in the shadow of Austro-Hungarian grandeur, a civilization steeped in music, philosophy, and the arts. Even as a boy, Schrödinger was drawn to patterns, the rhythms of poetry, the harmonies of sound, the symmetry of equations. His mind was both artistic and analytical, capable of holding logic and wonder in the same breath. When he studied physics at the University of Vienna, he absorbed the works of Boltzmann, Planck, and Einstein, not as rigid doctrines but as living ideas, questions waiting to be reborn. He would later write that he was never satisfied with mere calculation. The true task of science, he believed, was to see through the veil, to find unity behind appearances. It was this hunger for unity that would one day lead him to the equation that bears his name. But long before that, the young physicist wandered through ideas like a traveler through shifting landscapes. He taught at small universities, debated philosophy late into the night, read Goethe, Spinoza, and the Indian sages. The boundaries between physics and metaphysics blurred in his thoughts. He did not separate matter from meaning or energy from experience. The universe, he felt, must be one continuous whole, a single wave of being. By the 1920s, that belief was under siege. The quantum discoveries of Planck, Einstein, and Heisenberg had revealed a world of discontinuity, of jumps and probabilities. Schrödinger admired their brilliance, but felt an unease that went deeper than scientific disagreement. A universe ruled by chance seemed to him an incomplete picture, an unfinished sentence in nature's language. He could not accept that the foundations of reality were built on randomness. For him, beauty and coherence were not luxuries but necessities of truth. The task is, he once said, not so much to see what no one has yet seen, but to think what no one has yet thought about what everyone sees. In 1925, that task became his obsession. Inspired by Louis de Broglie's bold hypothesis that matter behaves like waves, Schrödinger began to imagine electrons not as particles darting around a nucleus, but as waves of energy, oscillating in harmony. If light could be both wave and particle, why not matter itself? Somewhere between mathematics and imagination, he glimpsed a vision of the atom not as a miniature solar system, but as a standing wave, like a violin string vibrating in discrete modes. Each vibration, he reasoned, corresponded to a specific energy level. The atom's structure, then, was not mechanical but musical, a resonance of existence. The search for the equation that could describe this resonance consumed him. That winter, he retreated to the Swiss Alps, seeking the solitude that only mountains can give. The snow outside lay thick and silent. The air was thin, pure, and full of stars. Inside a small wooden cabin, Schrödinger filled page after page with symbols, transforming intuition into mathematics. His companion during those weeks was not a team of assistants or an array of instruments, but thought itself, disciplined, luminous, relentless. Somewhere between inspiration and exhaustion, he found what he was looking for. The equation emerged as if it had been waiting all along. It linked energy, momentum, and the curvature of the wave, a continuous law describing how the wave function of a system evolved in time. In its compact form, it seemed almost simple. TSI equal to psi I T psi equal to H psi. Yet within those symbols lay an entire universe. Every atom, every molecule, every form of matter followed this rhythm. It was as though Schrödinger had written down the sheet music of reality itself. When he published his results in 1926, the effect on the scientific world was immediate and electric. The equation worked. It explained the spectral lines of hydrogen with exquisite accuracy. It predicted chemical bonds, atomic shapes, and energy levels that matched experiment after experiment. In one stroke, Schrödinger had united the fragments of quantum theory into a single symphony. The chaos of probabilities now had form. The discontinuous quantum jumps of Bohr's model became smooth waves of motion. His contemporaries called it wave mechanics, but to Schrödinger it was more than mechanics. It was meaning. Heisenberg, the young German physicist who had built his own matrix mechanics, was stunned. The two approaches seemed different, yet when Paul Dirac compared them, he found they were mathematically equivalent. They were two languages describing the same unseen reality, one algebraic, the other geometric. Nature, it seemed, could speak in more than one tongue. The rivalry turned to revelation. The new physics was not a chaos of theories but a chorus of perspectives, each completing the other. Schrödinger's fame spread quickly. His lectures drew crowds, his name became synonymous with elegance and clarity. Yet even as he stood in triumph, he was uneasy. Others were interpreting his equation in ways he found alien. Max Born, examining the mathematics, proposed that the wave function did not describe a real wave of matter, but a cloud of probabilities. The amplitude of the wave, Born said, when squared, gave the likelihood of finding a particle in a certain place. The wave was not physical, it was informational. To Schrödinger, this was heresy. He had not spent sleepless nights in the Alps to replace reality with statistics. He wanted to describe what is, not what might be. He resisted fiercely. In letters to friends, he complained that the new interpretation turned physics into a game of chance, stripping nature of substance. For him, the wave function was real as the sea, whose surface ripples with energy unseen but undeniable. The electron, he believed, was not a point but a spread of being, a continuous field that extended through space. The mathematics of probability was a shadow, not the substance. Yet he found himself increasingly isolated. Bohr and Heisenberg, the architects of the Copenhagen interpretation, insisted that physics must confine itself to what can be observed. Questions about what really exists, they said, were metaphysical distractions. Observation, not existence, was the foundation of reality. The philosophical clash between these giants was as dramatic as any battle in science. Schrödinger stood for continuity, Bohr for complementarity. Schrödinger saw unity, Heisenberg saw indeterminacy. Their debates were not about numbers but about truth itself. What is real when no one looks? Is the universe objective, or does it depend on the observer? Schrödinger's answer came in the form of a paradox, the now legendary cat in the box. It was his protest against the notion that observation creates reality. If quantum mechanics were applied to large systems, he argued, absurdity followed. A cat could be both alive and dead until someone opened the lid. The thought experiment was meant as a critique, but it became a symbol of quantum mystery. The paradox that haunted him would become the most famous image in all of physics. Even as debates raged, Schrödinger continued to refine his ideas. His wave equation blossomed into a framework for understanding molecules, solids, and even the foundations of chemistry. The new field of quantum chemistry was born from his mathematics. Chemists who once struggled to explain bonding now saw it as a dance of overlapping wave functions, where atoms joined not by hard collisions, but by interference and resonance. In laboratories from Berlin to Cambridge, the unseen world began to yield its secrets, guided by the quiet rhythm of Schrödinger's formula. But Schrödinger himself was never satisfied with purely scientific success. The deeper he delved into quantum theory, the more he felt that physics alone could not answer the ultimate question: what is the nature of reality? He saw patterns in biology, in consciousness, in the organization of life that reminded him of the coherence in the quantum world. Matter and mind, he suspected, were not separate categories but aspects of one underlying unity. "The world is given to me only once," he wrote, "not one existing and one perceived. Subject and object are one." This conviction placed him outside the mainstream. In an era when physics was becoming increasingly specialized and mathematical, Schrödinger remained a philosopher-poet, speaking of unity and consciousness, while his peers focused on measurement and prediction. Yet his holistic vision would later inspire entire generations of thinkers, from biologists exploring the genetic code to philosophers searching for a new relationship between science and spirit. His genius lay not just in the equations he wrote, but in the courage to ask questions beyond them. By the end of the 1920s, Schrödinger had helped build the foundation of modern physics. Yet he felt more alienated than triumphant. The world hailed him as one of the creators of quantum mechanics, but the version of reality that emerged from it was not the one he had dreamed of. His waves had been reduced to probabilities, his harmony drowned in randomness. Still, the equation endured, stronger than interpretation. It became the cornerstone of atomic and molecular theory, an indispensable tool for every physicist and chemist who followed. In the years to come, the same equation would shape technologies Schrödinger himself could scarcely imagine: lasers, semiconductors, quantum computers. His dream of an underlying order found expression not in philosophy, but in the circuitry of civilization. Yet even as his mathematics conquered the material world, the philosophical question he raised continued to echo: is the wave real or only the knowledge of it? Does the universe exist independently or does consciousness complete it? For Schrödinger, genius was not about certainty, it was about vision. He looked into the unknown and saw coherence where others saw contradiction. He built bridges between physics and metaphysics, between the seen and the unseen. His genius lay not merely in solving problems, but in redefining what a problem could be. In an age when science abandoned meaning for measurement, he insisted that meaning still mattered. He wanted the universe to make sense, not only mathematically, but existentially. And so, as the age of quantum uncertainty deepened, Schrödinger became its most reluctant prophet. He had revealed the music of the atom, yet the melody it played was not one of order but of possibility. Still he listened, and through his listening humanity heard the universe differently. His genius was not in ending the mystery, but in giving it form. He showed that beneath the turbulence of probabilities lies a harmony so subtle that only imagination can glimpse it, and in doing so he transformed both science and the soul of human inquiry. By the early 1930s, Erwin Schrödinger's name had become legend. His equation had changed the world, yet the man himself seemed increasingly uneasy within the empire of uncertainty he had helped to build. He had given physicists the most accurate mathematical tool ever conceived, but he had not found the philosophical peace he sought. The more the scientific world celebrated his triumph, the more he retreated into solitude and reflection, asking questions that no equation could answer. If the universe was truly governed by probabilities, where did purpose live? If reality was a superposition of possibilities, what did that mean for life, for mind, for God? In Vienna, his lectures drew overflowing halls. Students listened not only to the physics, but to the cadence of his voice, calm and lyrical, weaving mathematics with metaphors of waves and harmony. He spoke of the atom as music, of existence as rhythm. He was unlike any other scientist of his time, an orator of wonder in a field increasingly dominated by logic. Yet behind his composure lay tension. He felt misunderstood by his peers. Bohr and Heisenberg were redefining the meaning of reality through the Copenhagen interpretation, while Schrödinger watched his own creation transformed into something alien. To him, the wave function was real, a continuous field of being. To them, it was only a probability tool, collapsing the moment consciousness looked. The gulf between them widened until it became philosophical. Bohr's universe was participatory, Schrödinger's was complete. He traveled across Europe seeking clarity, lecturing in Zurich, Berlin, and Oxford. Everywhere he went, he was honored. Everywhere he felt alone. The fame that surrounded him after 1926 was both blessing and burden. He was feted as one of the founders of quantum mechanics, yet he could not accept the indeterminacy it enshrined. Einstein, who shared his discomfort, became his closest intellectual ally. The two men exchanged long letters, filled with admiration and frustration. Einstein's lament, "God does not play dice with the universe," echoed Schrödinger's conviction that beneath probability must lie pattern, beneath chance must lie coherence. They dreamed of a deeper order, a hidden layer of reality where the dice of the quantum world would be revealed as the steps of an unseen dance. But the times were changing. Europe was darkening under the shadow of fascism. The universities of Germany and Austria, once centers of freedom, were becoming instruments of ideology. Schrödinger, who valued independence above all, felt trapped between conscience and survival. In 1933, when Hitler came to power, Schrödinger resigned from his position in protest. He could not serve a system that demanded allegiance to false certainties. His decision cost him his country, his security, and his peace. That same year, the Nobel Prize came, shared with Paul Dirac, for the discovery of the new wave mechanics. The honor was immense, but the timing bitter. As his homeland descended into intolerance, the man who had redefined reality became a refugee from it. He moved first to Oxford, then to the Institute for Advanced Studies in Dublin, seeking a place where he could think freely again. Ireland welcomed him with quiet dignity. In Dublin he found not fame but space, a small office, a modest staff, and the freedom to wander through the labyrinth of ideas that had haunted him for decades. There, amid rain-washed streets and the Atlantic wind, Schrödinger turned his attention to life itself. If quantum theory could describe the smallest building blocks of matter, could it also explain the structure of living things? Was the order of biology merely an extension of the order he had glimpsed in physics? Out of that question grew one of the most extraordinary books ever written by a physicist, What is Life?, published in 1944. It was short, lucid, and profound. In it, Schrödinger proposed that the secret of heredity lay not in chemistry alone but in quantum order, in what he called a periodic crystal carrying genetic information in a stable yet flexible pattern. His vision anticipated, by nearly a decade, the discovery of the DNA double helix. The young scientists who read his book, among them James Watson and Francis Crick, later said it inspired them to search for the physical basis of the gene. Schrödinger, seeking meaning beyond physics, had unknowingly pointed the way to molecular biology. Yet even in that triumph, his deeper purpose was philosophical. He wanted to show that life was not an exception to the laws of nature but their fulfillment. Entropy, the tendency toward disorder, might dominate the inanimate world, but living systems created negative entropy, islands of order in the chaos. To him, this was not defiance but participation, life as the universe becoming aware of itself. He saw in biology the same principle that guided quantum physics: unity within multiplicity, coherence within uncertainty. The wave and the organism, he believed, were expressions of the same cosmic harmony. In his later years, Schrödinger became increasingly drawn to Eastern thought, especially the philosophy of the Upanishads. There he found an echo of what quantum physics had suggested, that all distinctions between observer and observed, self and world, are illusions. The same consciousness, he wrote, shines through all beings. There is only one mind, he said, the mind of the universe, of which we are fragments. To many of his Western colleagues this sounded mystical. To Schrödinger, it was the most natural conclusion of science. If the act of observation influences reality, then consciousness cannot be separate from the cosmos it observes. Physics and philosophy, long estranged, were reunited in a single vision. He would walk the green hills outside Dublin, reflecting on how far the journey had taken him, from the mechanical certainties of Vienna to the probabilistic mysteries of the quantum world, from the harmony of atoms to the enigma of awareness. He had seen the limits of both logic and faith. He had given humanity an equation that could predict everything and explain nothing. And so he turned inward, toward the mystery that mathematics could not touch. He believed that understanding reality required not just observation but participation, not just intellect but insight. He called this unity non-dualism, the recognition that the knower and the known are one. For Schrödinger, genius was never about accumulation of facts, it was about the courage to synthesize. He had lived through revolutions of thought and politics, yet he never stopped seeking wholeness. Even in exile, his mind remained a sanctuary of curiosity. He would write essays on color perception, on consciousness, on ethics, moving effortlessly between disciplines. He refused to accept the compartmentalization of knowledge that defined modern academia. To him, truth was a continuum, from physics to poetry, from biology to metaphysics. Every law, every equation, every pattern was a verse in the same cosmic song. He once described his life as an attempt to see the unity behind multiplicity. That unity, for him, was not abstraction but experience, the direct awareness that all things arise from a single field of being. The quantum world had shown him that separation is an illusion. The philosophical world had taught him that awareness is the bridge. He spent his final decades writing, teaching, and thinking about this unity, while the world around him plunged deeper into specialization and technology. The irony was not lost on him. The physics that had revealed the interconnectedness of all things had also fragmented human understanding into narrower and narrower silos. He hoped that someday science would rediscover its soul. As the years passed, his body weakened, but his curiosity did not. Even in illness, he read voraciously, still questioning, still wondering. He spoke often of time, not as a line, but as a web, where every moment touched every other. He suspected that the flow of time itself was an illusion born of limited consciousness, that the quantum world, timeless and simultaneous, hinted at a deeper order where past and future were one. To him, death was not an ending but a return to that larger unity. The plurality that we perceive, he wrote, is only an appearance, it is not real. It was both a scientific and a spiritual conviction, born of a lifetime spent tracing the edge between probability and purpose. When he died in 1961, at the age of 73, he left behind no grand laboratory, no empire of students, but a legacy that transcended disciplines. His wave equation remains one of the cornerstones of physics, used daily by scientists who may never have read his philosophical writings. Yet those writings are where the full measure of his genius lives. He was a bridge between worlds, between numbers and meaning, between Western logic and Eastern insight, between science and the soul. He refused to let knowledge become mere calculation. He insisted that behind every measurement lies mystery, and that to deny that mystery is to deny the essence of reality itself. Today, in the age of quantum technology, when Schrödinger's mathematics drives computers, communication, and medicine, his deeper questions return with new urgency. What does it mean that information and reality are intertwined? If observation shapes existence, what role does consciousness play in creation? Modern physics, with its quantum entanglement and multiverse hypotheses, continues to echo the questions Schrödinger first asked under the alpine snow. His vision, that the universe is one vast vibrating field of possibility, feels more relevant than ever. The boundaries he sought to dissolve between science and spirituality are dissolving again. Neuroscience, cosmology, and philosophy all circle the same mystery he glimpsed, the unity of being, Perhaps that is the true measure of his genius, not that he solved the mysteries of the quantum world, but that he revealed how deep they go. He taught humanity to see uncertainty not as ignorance but as invitation, to accept that the quest for understanding is endless because understanding itself is alive. He showed that probability and purpose are not enemies but reflections of the same truth, that the universe is creative, spontaneous, and conscious of itself through us. In the end, Schrödinger remained what he had always been, a listener. He listened to the equations until they sang, to the atoms until they spoke, to existence until it whispered that it was one. He had sought to make sense of a universe built on probabilities and discovered instead that sense itself is part of the universe's design. The cat in the box, the wave in space, the mind in matter, all were fragments of the same enigma. And though he never found the final answer, he gave the world something greater, the courage to keep asking. His life stands as a reminder that genius is not the possession of knowledge, but the ability to dwell within mystery without fear. In the language of quantum mechanics, he might have said that the observer and the observed are entangled, that to know is to become. Schrödinger became part of the very reality he studied, his consciousness woven into the fabric of the universe he tried to describe. His equation endures, his cat still purrs in paradox, and his thought continues to ripple through time like a wave that never collapses, a harmony that never ends. Erwin Schrödinger changed the way humanity thinks about existence. He did not banish uncertainty, he made it beautiful. He did not destroy mystery, he gave it meaning. In a universe of probabilities, he taught that the greatest certainty is wonder itself. In 1935, in a quiet Austrian study filled with books, light, and the gentle hum of thought, Erwin Schrödinger conceived one of the most haunting images in the history of science. A cat trapped in a box, suspended between life and death. He never intended the creature to be real. It was born of frustration, a protest against what he saw as the absurd consequences of quantum theory when stretched beyond the subatomic world. Yet that imaginary cat would outlive its creator, stalking through decades of philosophy, physics, and popular imagination as a symbol of the limits of human understanding. The thought experiment was simple, but its implications were staggering. It forced humanity to confront an idea almost impossible to accept, that reality itself may not be definite until we look. Schrödinger's cat began as a response to the Copenhagen interpretation of quantum mechanics, championed by Niels Bohr and Werner Heisenberg. According to their view, particles such as electrons or photons existed in a superposition of states, not one thing or another, but many possibilities at once, until measured. The act of observation collapsed the wave function, forcing the system to choose a single outcome. For the tiny world of atoms, this strange behavior seemed acceptable, even if mysterious, but Schrödinger wanted to expose how bizarre it became when applied to the macroscopic world, the world of tables, people, and cats. He imagined a sealed steel box containing a living cat, a radioactive atom, a Geiger counter, a vial of poison, and a hammer mechanism. If the atom decayed, the counter would trigger the hammer to break the vial, releasing the poison and killing the cat. If the atom did not decay, the cat would live. Quantum theory said that before observation, the atom was in a superposition, both decayed and undecayed. Therefore, the cat, whose life depended on the atom, must also exist in a superposition, both alive and dead until someone opened the box. It was an idea that defied common sense. Schrödinger's point was not to suggest that cats could be in such states, but to reveal the incompleteness of a theory that led to such conclusions. He wanted to show that something must be missing, some boundary between the quantum and classical worlds, some transition point where uncertainty becomes reality. Yet the paradox refused to fade. Instead of clarifying the problem, it deepened it. The cat became an ambassador of contradiction, forcing philosophers and physicists to admit that the act of observation is not passive, but participatory, that knowledge and existence may be intertwined. Over the years, Schrödinger's cat grew beyond physics into a symbol of human perception. It represented the unsettling truth that what we call reality might depend on our awareness of it. The question, is the cat alive or dead, became a meditation on consciousness itself. If observation determines outcome, then what counts as an observer? Does it have to be human? Could a measuring device suffice? Could the cat itself, aware in its own limited way, be the observer that decides its own fate? The lines blurred between science and philosophy, between matter and mind. Even Schrödinger could not escape the irony that his satire had become a cornerstone of the very theory he questioned. As technology advanced, experiments began to approach the boundary he imagined. Physicists created systems where atoms, ions, and even tiny molecules behaved like Schrödinger's cat, existing in superpositions of states, until measured. Quantum computers now rely on the same principle. Bits that are both 0 and 1, alive and dead, real and potential, until observed. The thought experiment that began as philosophical protest became the foundation of modern innovation. What Schrödinger invented as a critique became prophecy. His cat escaped the box, not as a contradiction, but as a key to the future. Yet the deeper meaning remains philosophical. Schrödinger's cat is not about life or death. It is about awareness and reality. It asks whether the universe has definite properties when no one is looking, or whether it waits for consciousness to illuminate it. It suggests that uncertainty is not a flaw in nature, but the essence of its creativity, that every moment of observation is an act of birth. The cat, both alive and dead, becomes a metaphor for every choice unmade, every possibility unrealized, every future waiting to be seen. It reminds us that the world we inhabit is not fixed but fluid, that reality is a canvas still being painted by perception. In the end, Schrödinger's cat did what all great symbols do. It transcended its origin. It began as a protest against paradox and became the embodiment of it. It showed that science, at its deepest level, does not banish mystery but transforms it into wonder. Schrödinger had not meant to create a myth, but he did, one that continues to haunt the boundary between the known and the unknown. The cat remains in its box, silent and eternal, a reflection of ourselves, poised between what we believe and what we dare to imagine, between certainty and possibility, between life and the unfathomable mystery that makes it worth living. When Schrödinger introduced his cat to the world, he did not realize that it would ignite one of the greatest intellectual battles in the history of science, a clash of minds and worldviews that would shape the meaning of reality itself. It was not a battle fought with weapons or armies, but with ideas, equations, and questions too deep for logic alone. On one side stood Albert Einstein, the guardian of determinism, convinced that the universe must obey reason and order. On the other side stood Niels Bohr and Werner Heisenberg, the architects of the Copenhagen interpretation, who believed that uncertainty was woven into the fabric of existence. Between them lay Schrödinger, torn between admiration for their brilliance and discomfort at their conclusions. What began as a scientific debate soon became a philosophical war about the very nature of truth. Einstein had helped give birth to quantum theory, yet he became its most famous critic. He had once revealed that light could behave as particles, but now he refused to accept a universe ruled by chance. For him, probability was not a principle but a sign of ignorance, a placeholder for knowledge yet to be found. God does not play dice, he famously said, echoing his faith in cosmic order. Bohr, calm and enigmatic, replied, "Einstein, stop telling God what to do." Their exchanges were legendary, conversations that shaped modern thought as deeply as any experiment. Einstein believed that every effect must have a cause, every particle a definite property whether observed or not. Bohr countered that such certainties belonged to the old world. In the quantum realm, nature did not reveal itself until questioned. Measurement, he said, was not merely a reflection of reality. It was an interaction that brought reality into being. Schrödinger watched this duel unfold with fascination and unease. He shared Einstein's instinct for determinism, but also admired Bohr's humility before mystery. He agreed that quantum mechanics worked, the calculations were perfect, but he doubted the story physicists were telling about what it meant. Could reality truly exist as a ghost of probabilities, waiting for human consciousness to solidify it? To him, such an idea turned science into magic. He sought a middle path, a universe where the waves of probability were real, where observation did not create existence but revealed it. Yet no one could find a bridge between these visions. The Copenhagen interpretation became dominant, not because it was understood, but because it worked. It predicted experiments with flawless precision. It built technology. It delivered results. And in a world rushing toward the future, results mattered more than understanding. Einstein refused to surrender. He designed thought experiments to expose what he called spooky action at a distance, the strange phenomenon where particles separated by vast distances seem to affect each other instantly. If quantum mechanics were complete, he argued, such non-local connections would be unavoidable. Bohr responded with equal conviction that nature simply did not conform to classical expectations. The debate stretched across decades, their correspondence filled with respect and tension. Each man knew he was confronting not just a colleague but a mirror, another mind reflecting the same search for ultimate truth from the opposite direction. In these exchanges, science became philosophy in its purest form, a dialogue about the meaning of existence, disguised as argument over equations. Schrödinger's own role in this battle was complex. His wave mechanics had given quantum theory its most elegant form, yet it was being used to support interpretations he found disturbing. He admired Einstein's clarity, but recognized that experiment after experiment favored Bohr's vision. The cat he had invented as satire now became a weapon in the war, invoked by both sides, misunderstood by many, but impossible to ignore. The image of a creature both alive and dead encapsulated the quantum dilemma better than any equation. It was the perfect paradox, both absurd and profound, illustrating the gap between mathematical success and philosophical comprehension. As years passed, younger physicists like John Bell and later generations revisited the battle through new experiments. They found that quantum entanglement, the very spooky connection Einstein had rejected, was real. Particles could indeed share states instantaneously across space. The universe was not local, not mechanical in the old sense. Reality, at its foundation, was relational, defined by interactions, not by isolated things. Bohr's humility proved prophetic, yet Einstein's demand for deeper understanding continued to inspire the search for hidden structures in nature. The battle, it seemed, had no victor, only an expanding horizon of mystery. Through it all, Schrödinger remained a symbol of the tension between mathematics and meaning. He had shown humanity the equation that ruled the quantum world, but he refused to believe that it ruled by chance alone. His correspondence with Einstein reveals a shared melancholy, two minds aware that the beauty of their discoveries had outpaced their comprehension. They were men who had seen too far and realized that the map of knowledge ends not in certainty but in wonder. Today, their debate continues in every laboratory and every philosophy seminar, where scientists and thinkers ask what quantum theory really tells us about the universe. Does observation collapse reality, or does it merely reveal one branch among many? Are there countless worlds where every possibility becomes real? Is consciousness the missing piece, or is it simply another quantum system entangled with the rest? The questions that once filled letters between Bohr, Einstein, and Schrödinger now fill the corridors of modern physics. In the end, perhaps both sides were right in their own way. Einstein's faith in order reminds us that truth exists even when unseen. Bohr's acceptance of uncertainty reminds us that our view of truth is always limited. Between them stands Schrödinger, the dreamer, who tried to reconcile their visions by giving the universe a wave to ride on, a wave that holds all possibilities until one is chosen. Their battle was never truly about dice or destiny. It was about humanity's longing to understand its place in the cosmos. Through that struggle, they revealed the most profound lesson of all, that knowledge is born not from agreement, but from the eternal tension between doubt and belief. And so, long after their voices fell silent, the argument continues, echoing across equations, experiments, and the endless curiosity of the human mind. A debate not about who was right, but about how vast and mysterious truth can be. Long after the debates between Einstein, Bohr, and Schrödinger had faded from the lecture halls, the strange thought experiment of the cat refused to die. It prowled through time, transforming from philosophical puzzle to scientific foundation. From metaphor to machine, the world had entered a new age, an age where the paradoxes that once existed only in imagination began to take physical form. The sixth chapter of this story belongs not to equations on chalkboards, but to laboratories glowing with lasers and circuits no thicker than atoms. It is the story of how Schrödinger's paradox came back to life as the driving force behind a technological revolution, one that would use uncertainty itself as a resource. In the decades following Schrödinger's death, physicists began to explore the full implications of his equation. The wave function that once lived only in theory was now being harnessed in experiments of astonishing delicacy. The invisible world that Schrödinger had imagined, where particles exist in superpositions of states entangled across space, was now being seen in the flicker of detectors and the interference of photons. The cat that was once symbolic began to take form in the quantum realm. Researchers created particles, molecules, even tiny mechanical systems that could exist in multiple states at once, only collapsing when measured. What had been philosophy was becoming engineering. The world was learning to live with the paradox rather than solve it. Quantum mechanics, once an intellectual rebellion, became the cornerstone of modern technology. Lasers, transistors, semiconductors, MRI machines, all operated on principles that defied classical logic. Every digital device that glowed in human hands carried within it the ghosts of superposition and uncertainty. Yet the greatest transformation came with the rise of quantum computing. The very same concept that had made Schrödinger uneasy, that a system could be in many states at once, became the key to unimaginable computational power. A quantum bit, or qubit, could represent both 0 and 1 simultaneously, allowing a computer to explore countless possibilities in parallel. The cat in the box had become a quantum processor, alive and dead, on and off, calculating realities beyond comprehension. It was poetic justice that the theory which once seemed to mock reason now built the architecture of the future. Physicists like Richard Feynman and later pioneers such as David Deutsch and Peter Shor began to envision machines that could use the rules of superposition and entanglement not as curiosities but as tools. The cat's uncertain fate became the logic of progress. Every time a quantum computer performs a calculation, every time an entangled photon transmits information instantaneously across space, Schrödinger's ghost smiles. His paradox had transcended mockery. It had become mastery. Yet even as technology advanced, the philosophical question remained: what does it mean that we can now manipulate uncertainty, that we can build devices using laws that no one fully understands? Have we solved the mystery, or have we simply learned to live inside it? Experiments with quantum teleportation and entanglement confirmed what Einstein had called spooky action at a distance. Information could travel between particles faster than light, or rather, outside the limits of space and time altogether. This did not violate relativity. It revealed that quantum reality operates on a level where distance itself dissolves. The universe, at its deepest layer, is not a collection of separate things, but a single, interconnected web. Everything is entangled with everything else. This realization began to reshape more than science. Philosophers, theologians, and artists saw in it an echo of ancient truths, that all things are one, that separation is illusion, that consciousness and matter are threads of the same tapestry. The cat, once trapped between life and death, became a symbol of unity. It reminded humanity that even opposites may coexist in the same reality, that existence is not binary but a spectrum of possibilities. Schrödinger's equation, once confined to the atom, began to whisper about the cosmos and the mind. The same principles that governed electrons seemed to echo in neural patterns and cosmic radiation. The boundaries between physics and metaphysics blurred once again, just as Schrödinger had always believed they must. The legacy of the paradox extended beyond machines and metaphors. It changed how humanity thought about knowledge itself. The quantum world taught that observation is never neutral, that every act of measurement changes what is measured. This principle began to influence fields far outside physics, from philosophy of mind to social theory to art. The idea that reality depends on perspective, that truth is not static but participatory, became part of the cultural imagination. The cat in the box became shorthand for ambiguity, for the coexistence of contradictions, for the fragility of knowing. In a sense, the cat had escaped its box, not through death or survival, but through transformation. It became a bridge between worlds, between the microscopic and the macroscopic, between physics and philosophy, between imagination and invention. Schrödinger's question, what is real, still lingers in every quantum laboratory, every data network, every reflective mind. His paradox continues to haunt not because it is unsolved, but because it may never be solved. It reminds us that mystery is not the enemy of progress, but its engine, that uncertainty is not chaos but potential. As humanity steps further into the quantum age, building technologies that would have seemed like magic a century ago, Schrödinger's cat remains its silent guardian, a symbol of humility before nature's depth. We now manipulate superpositions, entangle particles across continents, and simulate the birth of stars on quantum processors. Yet the fundamental question remains the same. When does possibility become reality? Where does observation end and creation begin? Schrödinger may have left the world believing that his cat was a philosophical jest, but time has shown it to be prophecy. His paradox foretold the shape of the modern world, a world where uncertainty is not a flaw but a foundation, where imagination becomes experiment, and where the invisible rules the visible. The thought experiment that once mocked the limits of understanding has become the key to transcending them. In the flicker of quantum code, in the hum of entangled photons, in the pulse of every device that carries the quantum signature, the cat lives on, neither dead nor alive, but eternal, a reminder that the universe does not yield to certainty, only to wonder. The legacy of Erwin Schrödinger did not end with his equation, his cat, or his debates. It continued as a quiet revolution that forever blurred the line between imagination and reality. His name became more than that of a scientist. It became a symbol of humanity's deepest confrontation with existence itself. The 7th chapter of his story is not about discovery, but about destiny. How one man's search for meaning reshaped the world's understanding of truth, and how his ideas still ripple through time, guiding thinkers, dreamers, and scientists toward the unknown. Schrödinger had sought to write the music of the universe, and though he did not hear the final note, his melody continues to echo across every field that dares to question what it means to be real. When he first published his wave equation in 1926, Schrödinger thought he was describing only the behavior of electrons. But as the decades passed, it became clear that he had touched something far more profound, the mathematical pulse of creation itself. The wave function, that elegant symbol psi, was not confined to atoms or molecules. It described possibility in its purest form. It became the bridge between the seen and the unseen, the finite and the infinite. Every time a particle moved, every time an atom interacted, the equation whispered its rhythm through the void. Schrödinger had revealed that reality was not a solid structure, but a shimmering field of probabilities waiting for consciousness to give it form. In that revelation lay both beauty and terror, for it suggested that the universe was not something to be observed from a distance, but something to be lived from within. He had once said that the world is given only once, not one existing and one perceived, but a single continuum of experience in which observer and observed are inseparable. Modern physics continues to circle this truth. Quantum field theory, chaos theory, and cosmology all trace their roots to the idea that the boundaries between entities are illusions. The same equation that describes an electron's orbit can, in principle, describe the entire cosmos. Schrödinger's insight became a spiritual equation as much as a scientific one. Everything that exists is entangled. Every event echoes through the whole. The wave function does not belong to the particle. It belongs to the universe. In the years after his death, the philosophy behind his work began to resurface in unexpected places. Neuroscientists exploring consciousness found themselves drawn to the same questions he asked. What is awareness, and how does it shape reality? Philosophers began to see in quantum mechanics a mirror of the mind, uncertain, nonlinear, capable of holding contradictions without collapsing. Artists, too, found inspiration in his paradox. Painters, filmmakers, and writers turned the cat into metaphor, the wave into poetry. Schrödinger's ideas had transcended science, they had entered culture itself. The equations that once filled chalkboards became symbols of human curiosity, of the fragile balance between knowledge and mystery. But perhaps the most extraordinary aspect of his legacy is how it continues to evolve through technology, the quantum computers of the 21st century, the encrypted communications that use entanglement, the delicate sensors capable of detecting the faintest vibrations in space-time. All are children of the equation Schrödinger gave the world. Each represents a step toward mastering the laws he uncovered, yet each also reveals how little we truly understand them. The deeper humanity dives into the quantum sea, the more it discovers that certainty remains out of reach. Schrödinger's lesson lives on in every experiment. Reality is participatory, and knowledge is never complete. Yet beneath all the machines and mathematics, there remains the man, the thinker who refused to separate science from philosophy, the physicist who saw divinity in equations. Schrödinger's final years were marked not by fame or controversy, but by contemplation. He lived quietly, walking in the Irish countryside, surrounded by the stillness he had once sought in the Alps. There, far from the laboratories and lectures, he returned to the question that had haunted him all his life: how can there be unity in a world of multiplicity? He concluded that consciousness itself is that unity, the thread that connects every fragment of existence. He saw the human mind not as a spectator of the universe, but as its instrument, its mirror, its voice. In that belief lay a profound optimism. For Schrödinger, uncertainty was not despair but invitation. It meant that the universe was still alive, still unfolding, still open to creation. His wave equation, born from the desire to find order, became a testament to freedom, a reminder that within every probability lies infinite potential. The cat that was both alive and dead became a symbol of possibility, of the countless futures waiting within each moment. Schrödinger had not destroyed reality, he had expanded it. He showed that mystery is not the enemy of truth, but its birthplace. Today, when scientists manipulate atoms one by one, when philosophers debate the nature of consciousness, when artists seek to capture the invisible, they are all walking paths that Schrödinger helped illuminate. His work remains a living dialogue between science and spirit, between reason and wonder. He taught that the universe is not something to conquer but to understand, not a problem to be solved, but a song to be heard. His legacy endures in every equation that seeks elegance, in every theory that searches for unity, in every mind that dares to imagine that reality is more than what it seems. In the end, Erwin Schrödinger's greatest creation was not an equation or a thought experiment. It was a vision of existence itself. He showed that life and matter, consciousness and energy, certainty and doubt are all expressions of the same cosmic rhythm. His journey through science was a journey through the soul of the universe. He began by asking how electrons move, and ended by asking what it means to be. Between those two questions lies the story of humanity's awakening, a story written not in words, but in waves. And as long as those waves continue to ripple through the cosmos, carrying the music of possibility, Schrödinger's voice will still be heard, quiet, eternal, reminding us that in a universe built on uncertainty, the greatest reality is wonder itself.